Welcome back, everyone, to the deep dive. For ages, it feels like, when it comes to building those large language models better, the recipe has always been pretty much the same, right? You just kind of shove in more data, make the
Yeah.
thing bigger, and like poof, magic happens.
Yeah.
And we've seen these huge companies pouring tons of resources into just making those first big training runs longer and longer. And then they try to fine tune these massive models to do very specific things.
Uh-huh.
Like get them to follow instructions or understand different kinds of information.
Yeah.
It's been this really powerful sort of two-step process.
It makes a lot of sense too, right? I mean, you would think just like intuitively, like if a human sees more information, like a human gets smarter.
Right.
So you would think that a model would get smarter. And we have this trend too that supports that called scaling laws,
Exactly.
which basically says like, yeah, bigger models trained on more data tend to perform better on tasks they haven't even been specifically trained for.
Right. But what if that core idea that more data, longer training always means better results?
Mm-hmm.
What if that's not actually like the whole picture? That's kind of the wild direction that some really cool new research is pointing towards. And that's actually what we're going to like really dive deep into today.
Okay.
Um,
Yeah.
We're looking at this paper that kind of throws a wrench into this idea that we all thought was so settled.
Yeah, that's right. This research, which is detailed in the paper 2503.19206v1.pdf, highlights something really unexpected. So basically pre-training a language model for a really long time, like exposing it to way more data than it's seen before, it doesn't always mean it's going to perform better when you later fine-tune it. Sometimes it can actually make it worse.
Yeah, which is a little bit of a head scratcher, right?
Okay.
You would think that all that extra learning, all that extra data would make it more powerful, more capable. Yeah.
For sure.
But the researchers are saying, well, not necessarily. So what's going on here? Well, they found something really interesting, and they're calling it catastrophic overtraining.
Yeah, catastrophic overtraining. So what is this exactly? It's basically when extending that initial pre-training phase, instead of it getting better at its job, it actually starts to hurt how well it does on those tasks you specifically fine-tune it for.
Okay.
Like imagine if you were sharpening a knife over and over again. Eventually, the blade is going to get so thin and so brittle that it'll probably just break when you try to use it.
Right, yeah. And I like that analogy because it really highlights like how counterintuitive this is. You would think more sharpening would make the knife better,
Exactly.
but it actually makes it worse. And this is not just some theoretical problem that's happening in like a research lab somewhere. They actually found evidence of this happening in real language models that people are using every day.
Yeah. Their work actually takes a look at this through a bunch of different ways. They look at what's happening with real models, they're doing controlled experiments, and even some theoretical analysis to try to understand what's going on. It's pretty thorough.
Okay, so what we're going to do today is we're going to try to understand why this catastrophic overtraining happens. Or
Yeah.
what are the hidden things that are going on inside that are making this rule that more data is better turned on its head?
Yeah.
And what does all of this mean for how we build and use these models in the future?
Exactly.
We're tailoring this deep dive for you. Let's just start with looking at the real world evidence because it's actually pretty convincing.
All right. So the researchers took a look at 3 different language models. These are Olmo 1B, Olmo 27B, and LLM 360 Amber 7B.
Okay.
And these are publicly available models too. And a really cool thing about them is that they have these intermediate checkpoints. And basically these are just like snapshots of the model at different stages of its training journey. So the researchers can go back and see, okay, how did training for this long versus this long actually affect the model?
Right. So they can sort of see how it's learning over time. So how do
Yeah.
they test these things?
So they took these snapshots at different levels of training, and then they did what's called post-training. And they did this in 2 different ways.
Okay.
First was instruction tuning, which is essentially teaching the model to better understand and follow instructions in natural language.
Okay.
And they used data sets like Anthropic HH and TULU.
Okay. So like real world data that's meant for training these types of models.
Exactly. The second approach they used was multimodal fine-tuning, and they used a framework called ELAV.
Okay.
And this is basically where you train the model to understand and respond to prompts that aren't just text, but images too.
Oh, wow.
So they weren't just looking at text-based stuff.
So they're really pushing it to be able to handle different kinds of input.
Exactly. And they were evaluating these models to see how they performed on the specific tasks they were being trained for. So their in-domain performance, or ID,
Yeah.
and also on more general knowledge and reasoning tests, which is their out-of-domain performance, or ODE.
Gotcha. So in other words, they're checking not just if it can do the one thing it was trained to do, but also if it's actually understanding things more broadly.
That's a great way to put it.
Okay, so what they find, where did this overtraining pop up?
The most striking results were with the ULMA 1B model. So they did instruction tuning on it with those anthropic HH and TLLU datasets, and there it was, catastrophic overtraining. And it showed up after they had pre-trained the model on more than like 2.5 trillion tokens.
Wow.
That's a ton of data.
Yeah, 2.5 trillion tokens. That's a lot of text.
It is a lot. So basically, after it went past that point, its performance started to drop.
Like a sudden drop-off?
No, it was more of a downward trend, not like a straight plummet. Its performance went down, not just on like the specific task of following instructions. It was giving less good answers based on the Alpi-Soval benchmark, but also on those more general knowledge and reasoning tests, like ARC, PIQA, and HelleSwag. You can actually see this really clearly in the paper. It's figure 2, and it shows that after they passed that 2.5 trillion token mark, the model, even after fine-tuning, started doing worse.
Yeah.
And what's crazy is the base model was still getting better at its original training task, but that improvement was making it harder for it to learn new stuff through fine-tuning.
So it's like the foundation was getting stronger, but it couldn't really build anything new on top of it.
It's a good way to put it.
So this wasn't just like a one-time fluke. They saw the same kind of thing happen in the multimodal experiments with LA.
Yeah.
Like its performance on the PIQA test actually went down with more training.
Huh.
And the difference in how well it did compared to the original model before fine-tuning on those general reasoning tasks,
Yeah.
it was shrinking.
So the fine-tuning wasn't doing as much.
Yeah, which means that the benefits of fine-tuning were kind of fading away the more it was pre-trained.
Okay, so this isn't just like one weird thing. It's happening across models, different ways of training them, and it's affecting how they do on specific tasks and how they do in general. It really shows you that this overtraining thing is a real problem, and it's something we need to look at.
It's not just some theoretical thing.
Yeah.
It's actually happening.
Yeah.
So why does this happen? What's the thing that makes this happen?
So that's where progressive sensitivity comes in. This is their explanation for what's going on with this overtraining thing.
Progressive sensitivity. Okay, let's try to break that down. What does that even mean in this case?
So basically, progressive sensitivity means that as you train a language model more and more, all those connections and weights inside, they get more delicate and easier to mess up.
Oh, I see.
And when you try to fine-tune it, you're making all these adjustments, and that can really throw things off. Imagine like a Formula One race car.
Okay.
It's super optimized to be fast on a specific track, but any little change to the car or the track can mess everything up.
Oh, right.
And it's the same with these models. The more you train them for that initial task, the harder it gets to fine-tune them without breaking something.
So it's like they get so good at one thing that they become kind of inflexible.
Exactly. It's almost like trying to teach a chess grandmaster how to play checkers. All that chess knowledge might actually make it harder for them to pick up the simpler rules of checkers.
That's a good analogy. So how did they figure out that this sensitivity was actually happening?
Well, they did some really smart controlled experiments. They realized that in real-world training, the rate at which the model learns, called the learning rate, it usually changes over time.
Right.
And this means that models trained for different amounts of time, they'll have different learning rates at the end. So it's hard to know if changes in performance are from how long they were trained or just because of the learning rate.
Right. It could be a bunch of things.
Exactly. So they wanted to figure out just the effect of the training time, not the learning rate.
Okay. So how'd they do that?
They trained smaller models for different lengths of time, but they kept the learning rate the same.
Okay.
And then to really see how sensitive these models were, they used something called Gaussian parameter perturbations.
Gaussian parameter perturbations. That sounds kind of complicated.
It sounds fancy, but it's actually pretty simple.
Okay.
It's basically just adding a little bit of random noise to all the model's settings. Like they're giving it a little nudge.
Okay.
And then they see how much this messes up the model's performance on the original task.
Okay.
And they measured this using something called C4 perplexity, which is a standard way to see how well a language model can predict the next word. Lower perplexity means it's doing better.
Okay.
So basically, they messed with the model a little bit and then saw how much it messed up the model's game.
Gotcha. So what happened?
They found that the model's performance on its original task, as measured by the C4 perplexity, it kept getting better with more training, which is what you'd expect, right? But then after they added the noise, its performance started to get worse beyond a certain point.
Really?
Yeah, it made this U-shaped curve, which you can actually see in figure 3 of the paper.
A U-shaped curve. So it gets better for a while, and then it starts to get worse.
Exactly. So at first, more training makes it better and more resistant to these little changes, but then at some point it actually becomes more vulnerable.
Interesting.
Like if you think about that race car again,
Okay.
the more you fine-tune it for a race, the easier it is for a tiny pebble to cause a big problem.
So they're getting more specialized, but also more fragile at the same time.
Yeah. And they also found that the size of that random change mattered too.
Okay.
Like bigger changes made this performance drop happen sooner.
So the more you mess with it, the faster it falls apart,
Yeah.
basically.
Yeah.
Okay, so how does this connect back to fine-tuning? Because fine-tuning is a more directed change than just adding random noise.
Exactly. And they saw the same U-shaped pattern for the C4 perplexity after they fine-tuned the models. So if you train it past a certain point, more training actually leads to worse performance on the original task.
Even though it's learning the new task, too.
Yeah.
Uh,
It's like the act of learning that new task, it's kind of like a bigger disturbance. And if the model's too sensitive, it ends up messing up the original stuff without really getting that much better at the new thing.
So it sounds like finding the right way to fine-tune is even more important when we're dealing with these really well-trained models that are so sensitive.
That's right. And that actually brings us to a pretty practical question. What do we usually do with learning rates during fine-tuning in the real world?
Okay.
Because as the paper points out, the learning rate isn't usually just left alone.
Right.
It's adjusted or tuned using a special set of data called a validation set. And this allows us to try different learning rates and pick the one that does best for the task we want.
So you're sort of finding the sweet spot for how fast it should learn.
Yeah. So the thinking is, even if a model's been pre-trained a lot and it's become more sensitive, we can maybe use a smaller, more gentle learning rate when we're fine-tuning.
Okay.
That way we're still teaching it the new stuff, but we're doing it carefully and hopefully avoiding that catastrophic overtraining.
So we're kind of tiptoeing around its sensitivity.
Exactly.
Uh-huh.
And the paper actually talks about this with figure 7, which shows you how the connection between that best learning rate and how long it's been trained can affect how it performs on both the specific task ID and its general abilities, O.
Okay.
So that figure shows us 3 scenarios. First, if that best learning rate basically stays the same no matter how long you pre-train it, we might see that performance drop in both specific and general abilities.
Makes sense.
Yeah.
If it's easy to break, but we're still making big changes when we're fine-tuning, then yeah, we're probably going to mess things up.
All right. The second scenario is if the learning rate needs to slowly decrease as you train it for longer,
Okay.
then you might just see the drop in those general out-of-domain abilities. So it might still be pretty good at the specific thing it was fine-tuned for, but it might not be as good at understanding and reasoning about things more broadly.
So it's kind of losing its flexibility,
Yeah,
which could be a problem.
it could be a problem, yeah. But the best case scenario is if that learning rate needs to drop really fast as pre-training goes up. So we're basically fighting against that sensitivity by using a much smaller, more careful learning rate.
Okay.
If we can do this, then maybe we can avoid that performance drop altogether.
So it's all about adjusting how we fine-tune based on how much it's already been trained.
Yeah, that's a good takeaway. Now, the researchers actually took things a step further and looked at the theory behind all of this. They used a simplified model of a 2-layer linear regression.
Okay. So they're going from real-world models and experiments to like a more abstract mathematical analysis.
Right.
What can this simpler model tell us?
So by using this simplified model, they could describe in a formal way how the model learns different features during pre-training. And think of these features as like building blocks that the model learns step by step. And the research suggests that it's this step-by-step learning of features that actually leads to the sensitivity we talked about.
Okay, so even in a simple model, the more it learns, the more fragile it becomes.
Yeah. And with their theory, they can define a specific point, an inflection point, where any change you make, like adding noise or fine-tuning, starts to hurt the model.
Is it like a tipping point?
Yeah, exactly. And when this tipping point happens, it depends on how big of a change you're making. Bigger changes make that point happen sooner.
So it's kind of like if you're building a tower, the more blocks you add, the easier it is to knock over.
Exactly. And the theory also shows that as you train it more, It learns new things, and each new thing creates another way for changes to mess things up.
It's like every new piece of knowledge also creates a new weakness.
Yeah, that's a good way to think about it. And they looked at fine-tuning through this theory too. They basically see it as the model learning a new set of rules, a new map that might not line up perfectly with what it learned before.
Mhm.
And they have a way to describe this mismatch too. They call it RR misalignment.
Okay.
And basically they found that this sensitivity really becomes a problem when the new task you're fine-tuning for is really different from what it was trained on originally.
Okay.
Theorem 4.6 in their paper, it shows that if the new task needs very different features from the ones the model learned before, then the negative impact on performance will just keep getting bigger.
So this is kind of like a mathematical proof that more pre-training can lead to this sensitivity and make the model worse.
Yeah.
So even in this simplified mathematical world, it shows that training it too much can make it harder to adapt to new things.
Exactly. And it really supports what they saw in their experiments with the real language models.
Yeah.
They also found some connections between their findings and other things we already know about in machine learning.
Really? Like what?
Well, there's something called catastrophic forgetting, where models forget what they learned before when you teach them something new.
Right.
It's not exactly the same, but it's similar in that the models struggle to hold on to what they already know. It's all about finding that balance between knowing a lot and still being able to learn new things.
Right.
And they compare their results with those scaling laws, too, the ones that say more pre-training always leads to better results.
Yeah.
And they're saying, well, it might not be that simple.
Hmm.
There's research that shows these U-shaped trends in performance as models get bigger and are trained more, which means that more isn't always better.
And this is important for people who are making smaller models too, right?
Yeah, because to get the best performance out of a small model, you often need to train it a lot.
Right.
And this research shows that doing that could backfire.
Interesting.
We need to be careful about overtraining, especially with those smaller models.
Okay, so they also talk about the connection between progressive sensitivity and something called progressive sharpening.
Yeah.
What's progressive sharpening?
So that's basically the idea that as a model trains the shape of its loss landscape, which describes how well it's performing, it gets more peaked or sharp around the current settings of its parameters.
Okay.
Like imagine a valley that's getting narrower and deeper.
Hmm.
And in a very simple case where the landscape has a specific shape, mathematically speaking, how sensitive the model is to those random changes is directly connected to how sharp the landscape is.
Okay.
So in that case, a sharper landscape means it's both more fine-tuned and easier to mess up.
Hmm.
But they actually found that just the sharpness of the landscape isn't enough to explain the performance drops they saw with those bigger changes or when fine-tuning.
So it's not just about the shape, there's something else going on.
Exactly. It's more than just the lost landscape getting sharper. It's like something's happening to how the model stores information as it trains more that makes it fragile.
So it's more like a fundamental vulnerability to changes.
Yeah.
Okay. This has been a really interesting look into this area of research with language models. So let's bring it all together. What's the big takeaway here?
The main thing to remember is that this idea of just giving more data to language models doesn't always mean they'll get better.
Right.
We've seen from experiments and from the math that there's this thing called catastrophic overtraining, which seems to be caused by progressive sensitivity.
So more pre-training doesn't always mean better results, especially when you're trying to teach them new things with fine-tuning.
Exactly.
You can actually make them worse.
And this is super important for anyone who's working with these models or even just trying to understand how AI is developing.
Yeah.
We can't just assume more data is better.
So what now? What do we do with this information?
Well, the researchers are suggesting that we need to find ways to deal with this sensitivity. Maybe by coming up with new techniques to make them more robust, or changing how we train them initially to make them more flexible. There's still a lot to figure out.
Yeah. This has been really thought-provoking and leaves us with one final question to think about. As we keep building bigger and bigger models, could it be that knowing when to stop training is just as important as knowing how to start? What does this sensitivity mean for the future of AI?
It's a big question.
It is. Well, thanks for joining us for this deep dive. It's been a pleasure exploring this with you.